Hello YouTube. Yes, for this video I have the air conditioner turned off, so hopefully we won't get as much noise as I got in my previous video. But anyways, so today we are going to be looking over basically this drawing right here. I think it would be a fun idea to make my own computer architecture. If for any other reason than just to understand how a computer works, and hopefully I can try to make something uh, that's competent enough to do something. So yeah, I basically just went on Wikipedia and copied in a bunch of assembly instructions, and we're gonna try to see if I could make a working CPU architecture. So how a CPU works basically is that there are three things. There's your ALU. This does math and stuff, uh, bitwise operators, that kind of stuff. I made four a 8-bit ripple carry adder subtractor, and I did make a video on that. So I have this already, and I made that out of transistors. But of course, for a CPU, you have to have more than that. Another thing you have is an accumulator. It's basically a register that can store the operands that your computer is working on. So how it kind of works is that your accumulator has something, and then that goes to the ALU, and so does something from RAM or whatever, and then you could output it like that. And your program counter, this is like another register thing, and that stores which kind of, from what I gathered, it stores what address you're on. So it's 0, 1, 2, 3, and it will increment for every cycle and instruction that goes through the computer. So for the purpose of just this picture, whatever, I'm basically having a 4-bit computer. Normally when you hear about computers, they're at least 8 bits. Like, for example, I have a Z80. This is a Z80. This is an 8-bit CPU. But it actually can address up to 16 bits of address, and that makes it more useful. But anyways, this can only address 4 bits. So there are 8 bits at each address. So how it works is that this is your ROM or it's your RAM. You can switch between both. I don't know if I'm explaining this right, but yeah, there's a RAM and there's a ROM. The RAM is used for storage of operands and stuff that you can read and write to, whereas the ROM stores your program that actually gets executed. And what it does is, in each of these cells of ROM or the RAM, there are 8 bits. So of those 8 bits, the computer interprets it like this. There are 8 bits, and the lower half of this is going to be the RAM address that this opcode is applying to, or it's going to be data if you're inputting a constant into the accumulator. So then you have your opcode, and what that does is your opcodes are basically the instructions. So these are just kind of arbitrary based off of how the CPU is wired. You could wire any one of these opcodes to mean any one of these instructions. It's just, I guess, just other circuits that are in here that actually interpret what to do. So how I have it is you have a few of them. You have add, subtract, store, load, branch if not 0, branch if positive. This is what I copied from Wikipedia. Branch if positive would be for if it could have a signed value using 2's complement. This 4 bits, so you're not. We're assuming that everything operating here is 4-bit unsigned integers. No floating points, no signed numbers, nothing like that. Though you could implement that with software, but with 4 bits, what are you going to do? You have 4 bits. So yeah, you have that, and then you have input, output, halt, which stops the CPU, and then your bitwise operators and or exclusive or not, and these really all you need is and or and not. Exclusive or is kind of just whatever, and then you have 2 other ones because this is 4 bits and you can get 16 instructions. Even though I don't know what to do for these 2, I can make it do whatever I want, I guess. So how this actually works is this will add data to the value in the accumulator. So what it's doing is like this is saying add, and the opcode is going to be 001 like it says here, and the data is going to be a RAM address. So this part of this is going to be a RAM address, and pretend that this is the RAM. It's going to say 000 or 0100 or whatever, and then let's say it's like 0100, and that's what 4. And then what it's going to do is it's going to look in the RAM and take whatever is in the RAM, whatever value is in the RAM, and then it will add that to whatever is in the accumulator. So it'll take whatever's in the RAM, add it to the accumulator using this, and then it'll store it back in the accumulator. Same for the subtract. It'll subtract the data from the RAM from the accumulator. So the accumulator equals accumulator minus whatever's in the RAM. And then you have store. So let's say you perform one of these and now you've added it and you want to store this in RAM. What the store is going to do is it's going to provide the opcode that's a store, and then it'll provide a RAM address, and it'll store the value of the accumulator into the RAM address. And then load will load a value from a specified address to the accumulator, and that's kind of how that works. And then there's also branch, branch if not 0. These are all branching. What branch does is it's going to jump to a specified address in program memory, and how I interpret this is that means that if it gets the branch instruction, let's say it's here in ROM and it says branch and then this here is 0, so it'll say oh I'll go back to 0. And then how this actually ends up working is that you go back to 0 and then you go back through until you get to where it says a branch, and then it'll branch back here. That is how a loop is implemented. So you're going all the way to the address where it says branch, and then it'll go back here, and then it'll keep doing that. Okay, problem is that is an infinite loop, which is not very useful. Sometimes it's useful, like these Arduinos have infinite loops, but really what you want is a conditional loop, because that allows you to do loops you could break out of, like for loops. And since it is a conditional branch, that's you could implement if statements with that. So it says branch if the accumulator value is not 0. This is just what I pulled from Wikipedia. You could have a branch if 0 or branch if something else. Just whatever circuit you want to make here, that's what it'll branch to. So let's say it'll go here, and if the accumulator is not 0, then it will branch. The nice thing is you can implement an if statement, like if you're saying if like x equals 3 or whatever, and you want to branch if it's if this is true, if x is equal to 3, then and x is like a RAM address for a variable. That's how you implement that. So you could x would be the accumulator. Yeah, if the accumulator stores. Okay, so the problem is, like, you have an if statement in like C or whatever, but in assembly that's like a bunch of different instructions. So like if x equals 3, okay, let's say x is a variable is an address in RAM. Okay, so to get x, you have to pull it to the accumulator, and then you have to subtract 3 from it. And so when you have subtract here, you can subtract data value from the accumulator. Okay, so then you need a constant data value. That's probably one of these instructions that I got to add, is to specify a constant data value. And then the accumulator equals the accumulator minus this. Okay, yeah, that makes sense. And then if that's 0, so you're subtracting 3, or which another thing, this could be -2, that adds issues. Yeah, you subtract 3 from x, and then if x is equal to 3, then the value in the accumulator will be 0, and you can branch to the specified address if it is 0. Okay, that was long and complicated, which is why people usually don't bother with low-level programming, but this is how I spend my time. So we have these other branches, and then we have the input, which is takes value from the input and stores it in the accumulator. Everything's stored in the accumulator. And the input, I'm just assuming this is also a register that you could just flip the values of. Yeah, this isn't exactly the von Neumann architecture or whatever it's supposed to be. This is kind of stuff I made up. Like normally these would be the same thing, unless you want to input and output at the same time, maybe. And then of course, getting to output, you output the value of the accumulator. So yeah, let's say the accumulator storing 4 bits, so this is 4 bits. Ooh. And what you could actually do with this is, this could be a sort of microcontroller type of thing, because this is like a port register that you would have in an Arduino. So instead of all these pins, you can only get 4, but you could use them just the same. You don't get PWM, you don't get analog, but you do get 4 bits of output and 4 bits of input. Interesting thing to think about there. And then we have halt, and halt will stop the program. How I interpret this is it's just going to stop the clock. That might be the way to do that. There's also a clock signal coming in here, which tells the CPU how fast it is, and that's how fast it's taking in, and the program counter goes up. And then of course we have your bitwise operators. These are important for certain things. How I have it is for it's the accumulator equals the accumulator and the data specified by the RAM address. So this is effectively a pointer, or it could be data if it's specified as a constant. So like we could have, for example, another instruction which is like and constant, and what that will do is, instead of interpreting this as a pointer to an address, it will interpret this just as a constant value. So that's another thing you could do. Though I don't think you need it, as long as you have some kind of that's like store constant, whatever. And what that will do, I'm not the best with abbreviations, but store constant, let's just say that this is the thing, like for example, this could be it. What it will do is you'll have the opcode that's a store constant, and the data is going to be the constant, and it'll store that constant in the accumulator, and then you could export that and go around. So yeah, assembly instructions are verbose. So, and the not doesn't even have an input or anything. It's the accumulator equals the accumulator not. Alright, so this is my attempt at trying to make a computer architecture. Like I said, 4 bits. Not a lot you could do with that. Another big thing that you kind of need for a lot of stuff, like for example, I was thinking about computing pi with a Taylor series, and for that it's like pi is equal to 4 plus or minus 1 over third plus 1 over fifth or something. Yeah, that's I'm not sure if that's right, but yeah, if you want to calculate pi, you have to do fractions, which are you're not going to get very far if you can't do floating point operations. So that's the issue here. And how floating point numbers work is that, let's say we have a float, and then you have a bunch of bits. Floating point numbers take up a lot of storage. They're like 32 bits or more. And like how it's like the first one is like the sign, and then the next are the exponent, and this is the mantissa, which is the part of the number. Mantissa is an interesting word. So like it's like negative 2 times 10 to the power of 4, whatever. So this is your sign, this is your mantissa, and this is your exponent. And it's all of this, but in a binary number, and the negative is 2's complement or whatever. It takes up a lot of bits. And my challenge is how to actually make something. Because what I'm trying to do is I'm trying to create a computer architecture. And that requires actually wiring this stuff up. We're not to just think about a programming, we're thinking about like, basically we're programming a computer by soldering. So there's a practical limitation. We can't have 32 bits. We could possibly have 8 bits. I mean, look at the Z80 right here. It has 8 bits. Let's actually take a look at this right here is a Z80, and you can see that, yeah, you can see that this Z80 has 16 bits of address lines, and it's all of these right here. These are the addresses. So this is all the numbers it can address. And then all the data lines are pulled down to ground, and what this means is that this is going to execute no ops. So it's not going to do anything. Yeah, that's what it's going to do. Absolutely nothing at all. And yeah, I had this where it could work. I actually posted a video about just this right here. And yeah, so I have that. And also, we could take another look over here while we're just taking a room tour. And we have this, which is just a pile of components. This right here is the stuff that I was working on. This is the full adder circuit. And this right here. This, like, look at this. This is a monstrous beast. This right here, this snake, is a 7-segment display driver. All these things I made videos about. If you watch them, or whatever. So, yeah, this is just to drive a 7-segment display. All that right there. This is my attempt at making a pixel addressable display. So is this one right here. And then this is a full adder. It's actually a full adder subtractor. And how you get an adder subtractor is you have all these full adder circuits, and then you have these right here, which are exclusive ORs. And if you turn these on, it will transform the adders into a 2's complement subtractor. And how it works is the display is just red here. So this itself is actually an arithmetic logic unit. It's missing some key features, particularly it just adds and subtracts, you really want bitwise operators. How I thought about implementing it was just putting a bunch of OR gates in parallel, like with these transistors, just making a bunch of OR gates and putting them in parallel. That would work. And then putting a bunch of AND gates and a bunch of NOT gates in parallel. And then that's should implement all the features necessary. So yeah, this is going to, so the ALU is going to be this. If I made it in discrete transistors, that is, it's going to be this plus a bitwise operators kind of thing, and that's like a shelf. And then above that, we're going to have registers and control circuitry, because it has to actually interpret instructions. And then there's going to be a program counter and the accumulator. And then there's like RAM and stuff. Yeah, so that's what this is. So this, or the Z80 over there, these are my attempts to make a computer design. Alright, so another thing is I've been programming stuff in C. I have an emulator of this, which I'll probably make the next video on. But for now, I hope you've enjoyed this video, and thank you for watching.